Let's go. Any questions or comments? We have wrapping up operations. Yeah, Yankee told me that he had trouble getting the normal ordering constant in the BRST operator, the minus C naught term. Did anyone else try it? Okay, so this is a serious assignment. Please try that. And if by next class people still have trouble, we'll do it in class. Okay, so okay, great. Now we have various very small things to do before we complete our discussions of chapters 1 to 6, basically, or 1 to 5. 1 to 5 of Polchinski. Let's do that, and then we have to take a decision about which way to go. Yes. Okay. So if you remember, at the end of the last class, we ended the last class more or less proving what I call the no-ghost theorem. Okay, the no-ghost theorem, by the way, is a limited theorem. It just says that on the world sheet, the BRST cohomology has no negative norm states, and moreover that the BRST cohomology is in one-to-one correspondence with the spectrum of light cone quantization. Note where it does not at the moment. Now you might wonder, why do we care? The world sheet is not immediately physical. Okay, of course the physical implication of this should be that the space-time scattering amplitudes that you will build out of this world sheet theory will all be unitary. Okay, and this has now been proved, as we discussed, by Ashok and collaborators. Just to, over the last, that it should work. There's some discussion in the last chapter of volume 1 of Polchinski, some fuzzy discussion for why it should work. It has the main ideas, but it's something that's been proved. The fact that this no-ghost theorem works, of course, is an integral element of that proof. So this no-ghost theorem, though it's for an auxiliary structure, namely the world sheet, is crucially tied to unitarity of string scattering amplitudes in space-time, so it's very important. Now, I wanted to understand these BRST cohomology classes just a little bit better. Okay, and yeah, question? Okay, so I wanted to understand these BRST classes just a little bit better, and so there were one or two things that we wanted to say. So you remember, right at the end of the last class, we started talking about states of the following form. Consider a state psi that is ghost vac, a ghost vacuum, and otherwise it's an arbitrary matter state. We've got a state psi that's a ghost vacuum and an arbitrary matter state. Now I want to understand what is the condition on such states, coming from the fact that the state must be BRST closed. Okay, so now let us remind ourselves what the BRST charge was. First, Q was sum over n Cn L minus n. Now we're going to use this oscillator language, which will be more convenient for this discussion than working with vertex operators, though of course it's equivalent. Okay, then there was a term which was, I'm going to write it down. If somebody has in their notes, you'll help me, otherwise I'll look it up in Polchinski. M minus n by 2 B minus m plus n Cn Cm Cn plus minus C0, right? Maybe there's one more term. Let me write it.
You just want the minus thing to be to the right.
I want the B minus thing. This is, I haven't at the moment said whether M is positive, negative. Okay, everything here is understood as oscillator normal ordered. So in every term, the ordering is set so that you put. But let me just get all the signs and so on straight. I'll quote it out of Polchinski. Cm Cn B minus, okay, good, and minus C0, and yeah, it looks good.
This is just the matter of
this was, yes, this Ln is Lm matter. Okay. So now let's take a state of this form and act on it with Ln matter, with QBRST. Okay? So what do we get? Well, let's look at the first term. In the first term, what we get is that anything that has a C, anything with n positive annihilates the state because it's in the ghost vacuum. Okay? Anything with n 0 or negative does not annihilate it. Because when I say ghost vacuum here, I mean the down. So C0 does not annihilate it. It makes it up. And of course, C minus n does not annihilate it. Okay? So we get C0. I'll isolate out the C0 part. C0 L0 plus C minus n Ln sum n is equal to 1 to infinity. Now what about these guys? You see, anything that has even one positive C will annihilate the vacuum, because if it's positive, because it's normal order, the positive guy acts on the right and will annihilate the vacuum. Okay, but it's impossible to have a set of 3 objects which add up to 0 and have no positive C unless all 3 are 0. But if all 3 are 0, we'll get 0 because C square is 0 m minus n. Yes. So we've got a bunch of C, 2 C's and a B. The indices all add up to 0. Okay? Now, even one of these indices is positive. Acting on the ghost vacuum, we'll get 0. Okay? Now, how can it be that there are no indices positive and they sum to 0? Only if all 3 are 0. But if all 3 are 0, this term is 0. Because C0 squared is 0, which is captured by the m minus n. Okay? So this thing annihilates the ghost vacuum. This thing does not. So it makes this L0 matter minus 1. Okay? So Q acting on this state gives you this on ghost vac arbitrary matter state is equal to 0. Now, C0 on ghost vac, well, I mean basically this part acts only in the matter state. So think of this as ghost vac tensor psi, where psi is the matter state. Okay? So this is the condition that L0, what have I written here? L0, minus 1. L0 matter minus 1 on psi matter is equal to 0. Also that Ln on psi matter is equal to 0 for all n greater than equal to 1. Right? Because this state must vanish. So coefficient of every C minus n must vanish independently. Because in the ghost sector, those are independent states. Is this clear? Therefore, we conclude that this state has the property that it's annihilated by all ln's with positive n. What does that mean for the dual operator? It's a primary. And it has L0 matter equals 1. What does it mean for the dual operator? It's a primary of dimension 1. This is something we anticipated long ago. We anticipated on general grounds. This is 1, 1 primary. So, this, if we look at states of this form, there are ghost vacuum times matter, and we want them to be, so I should have written this tensor psi. Then we conclude that psi m is dual to V, which is a 1, 1 primary.
Did you acting on this quantity is 0?
What acting on this?
You have started with a particular class of states already.
Yeah, I've started with the state such that B0 acting on the on this is
Yeah,
0.
but it is bound that you will get a total L0.
L0 equals this was total L0 equals 0, which was same as L0 matter. Yes. So this is a re-derivation of something we already knew, using the fact that the ghost vacuum has energy minus 1. Right, this is just, that minus 1 is just the statement that the ghost vacuum has energy minus 1.
And the lower one, Ln, was Q times Bn.
We've also checked this before using vertex operator algebra. You remember we looked at an operator that was of the form C times V.
Yeah, both the statements is coming from this same formula. This Q anticommutator Bm.
Yeah, exactly.
Both of them are the same.
Exactly. We looked at the following statement. We looked at the statement that Q acting on CV. We looked at the pole of that. Okay? And we found that this thing has no pole only if V was a matter primary. We checked that, right? That all singularities that had to start at 1. We've checked it before. This is it's the same thing, but perhaps even easier when we work with the oscillator. Okay? All good? Great.
And this is same as this Lisa one I said that, right? This
You weren't saying this, then I wasn't paying attention. So what did you say, please? Sorry.
Q anticommutator Bm is Lm.
Q anticommutator Bm is equal to Lm.
This is the identity you proved.
Oh, yes, we proved this at some point.
This one is clearly that.
But it's not so clear that this, what has that to do with, why will we ever get Q anticommutator Bm? Yeah.
We take this answer, take M to be positive, let's say.
Mm.
Let's say M is greater than equal to 1.
And you're saying this state is annihilated by, yes, you're absolutely right. These states are annihilated by Bm. Yeah, that's what you're using. Absolutely
This
right.
is on two formula.
Yeah, absolutely. So Indranil's got a good way of proving it. Saying, observe that all such states are annihilated by Bm for M positive.
Yeah.
It must also be annihilated by Q. And therefore, if we look at Q anticommutator Bm, it must be annihilated by Lm. From this, beautiful, yes, also right. Okay.
So the opposite statement that a primary in the ghost vacuum has to.
That if you look at the ghost vacuum,
Q closed and being in the ghost vacuum has to be
primary, yeah, absolutely. Okay, we have 3 completely identical ways of saying the same thing. Of course, they're all the same. Fine. Now, let's go on. We've checked that ghost vacuum times psi m, which is a primary operator, is Q closed. I want to know when is it that ghost vacuum times psi m is also Q exact. Okay, suppose I take something of the form ghost vacuum times psi m, which is primary. Okay, it's Q closed. I want to know when is it the case that it's also Q exact. Okay. Now let's check this out. Well, I'll give you we'll do it in well, let me first give you a formal argument and then we'll try to see it more hands-on. The formal argument goes as follows. Look, I want to first claim the following. I want to first claim that suppose psi m is equal to L minus k of some chi. These statements are all in the matter sector. So psi matter. I'm removing the matter. Everything here is in matter sector. Suppose psi is L minus k of psi. Okay? Then I want to claim that this quantity is Q exact. Then exactly. So the formal argument goes as Indranil anticipated. Okay? The formal argument goes, let's compute psi psi. We'll write this as psi L minus M chi, which is equal to Lm psi chi, using the fact that Lm is L minus M dagger, which is equal to 0 because psi was primary. Okay? So what we've just shown is that if an operator is both primary and a descendant, if some descendant operator happens to be annihilated by all the lowering operators, then it has to be null. Okay? So this object here is both primary and descendant, and therefore it has to be null. We just proved that.
But any Q exact state is null.
See, at the moment we're not saying, given that this state is this, we want to show that it's Q exact. Okay? So I've taken a form of a state and I want to prove that it's Q exact. I'm going to use what you just said. Okay? So the formal argument goes as follows, the slick argument goes as follows. Now we've proved the no-ghost cohomology. We've proved the no-ghost theorem, which means that in the set of all Q closed states, okay, in the set of all Q closed states, all inner products, the inner product is positive definite in equivalence classes. Moreover, if you just have a Q variation within an equivalence class, we know that that gives you a null state. So the no-ghost theorem is equivalent to saying that if you look at the set of all Q closed states, the inner product has a positive definite part and a null part. Inner product matrix is a set of positive definite and then a set of zeros, and the zeros correspond purely to the Q exact. Therefore, since this thing is zero norm, it must be Q exact. This is the kind of slick mathematician's argument. And it's a good argument. But of course, you could also just check it more carefully. Okay? You could try to construct by just trying to construct a state. Okay? Such that this psi is psi, which is of this form, is Q of something. Okay? So, suppose you wanted to construct such a state, what would you choose? So let's just do it so that we feel confident. Suppose I wanted to construct such a state, what would I choose? Well, I would choose a state. See, this psi here has ghost number, with the convention that the ghost vacuum has ghost number 0. It's not always the most convenient convention. Okay? But with that convention, this psi here has ghost number 0 because it's the same as ghost vacuum. Therefore, this psi here also has ghost number 0, but it has to be Q of something.
That can, wait a minute, what was the argument? Psi was ghost number what? 0.
0. We're putting a convention. Ghost vacuum, let's say, is ghost number 0.
Okay.
Okay.
Sorry.
Yeah. So then this thing is a ghost vacuum state.
It's in the same class you are saying.
Yeah, it's in this class. If we take ghost vacuum, so it's got a ghost number 0. So we want to check that something that is of the form L minus K chi is equal to Q on some phi. We want to check that this is true. Okay, we want to check that this psi is equal to this, and also that psi is annihilated, is primary.
But in this convention, is it just the stress tensor is going to be 0 with 0 charge under ghost
Yes.
number?
Yes, stress tensor has nothing to do. Yes, 0 charge and ghost.
what is the identity operator charge?
0.
This is what I want, but this is same as this goes back on 0.
That's just some normalization. Actually, oh, you mean?
I mean, I want identity operator to be 0.
Okay, let the ghost vacuum have charge A.
Okay.
We can figure out what it is. It's charge 1 actually, or whatever it is. We can figure out what it is. It's a matter of normal ordering constant. Okay, let it have charge A, but that doesn't matter for this argument. This thing has to have charge A minus 1 because Q has an explicit C.
Yes. That I agree.
That's all that we need. Okay, so this phi here has to be built with one more B than a C. One more B oscillator than a C oscillator. Okay, so what could we get? We could get either Bm times zeta m, where zeta m is purely matter state.
One more B than C.
One more B than C. So one thing is to have one B and no C's. Another thing would be to have two B's and one C. Okay? Now, we want the kind of state such that when we act on it with Q, will give us something that's in the ghost vacuum. Okay? So, a state with one B and this thing will work. Because either this C0 or the C's from here. Okay? That will work, but something with two B's and one C will not work. Why? Because you see these two B's and one C, so that they, I'll call this minus m, so that they give you something non-trivial or carry negative indices, because otherwise they would annihilate the ghost vacuum part. Okay, so there would be three operators here, two B's, let's say, and three operators, all which carry negative indices. We want them all to be killed by the action of presumably this term. But that can't work because these can't all have positive indices, because they sum to 0. So the only thing that's in our hands basically is this kind of object. So this is the kind of this is what we have to play around. Is this clear? So if this thing is Q of something, it should be Q of something like this. Okay. Now, so let's try AM, C, AM, okay, whatever, some BM chi m, sum over M, some unknown matter states, and act Q on it, and see what we get. Okay? In fact, let's just set a particular M. Let's just take a particular M. Okay? And act Q on it. And then we can take a linear combination of such things. Okay, so we act Q on it. The only term that will contribute is with Cm. Okay, say M is not 0. If M is 0, by the way, it annihilates. Yeah, so M is not 0. So Cm, so we get L minus M of chi m. And that's done it. Okay, so we've shown that Q acting on this is L minus 1 m, which is what we wanted to show. Okay, so we don't need slick arguments. These constructions are very simple because the form in the end is very simple in terms of oscillators. Okay, but of course slick arguments are a bit faster. So first we've shown the following. What have we shown so far? We've shown that stuff of this form is Q exact. Now I also want to prove that there are no other Q exact states other than this one. But we've just shown it. You see, the only way that we can build something that is ghost vacuum is starting with something with the ghost number, one B charge more than ghost vacuum, minus 1, ghost number of vacuum minus 1. You could have had many possibilities, but as we just argued, the only thing that would give you something ghost vacuum is just with some B minus M. Okay? And we've just acted with Q on this and seen. So the only states of the form that we looked at, which were ghost vacuum times I matter, okay, that were Q exact, were states of this form, states that are both primaries and descendants. Okay, excellent. So now if we restrict our attention to states of this form, okay, if we restrict our attention to states of this form, then we have shown that states of this form.
Can I write this L minus K anti-commutator of Q and B K, P K B minus K, and then Q annihilates this guy, so it's Q of B minus M of.
That's probably good. Let's try. L minus K is equal to anti-commutator of Q and B minus K, and then you have Q on B minus K. B minus K chi is equal to plus B minus K Q chi. And now,
if I use Q acting on chi is 0.
Right. No, but we want to show yeah.
But you are looking at states only in this class. For Q, these are three closed states.
Well, yeah, if Q on some Q on
But it will automatically be Q closed, right? Because if it's Q on something is Q on something, and from Q squared is equal to 0. We just want to show that things of this form are Q closed. Maybe you can prove this. I'm not 100% sure. Okay. Oh, we see the argument. We see the result anyway, right? Okay. Now, the final thing I want to show is the following. I want to show that every Q cohomology class has one representative of this form. Okay? Once we have shown this, in order to deal with Q cohomology classes, we can work with a simpler problem. That is, work with states of the form ghost vacuum times matter 1 primary. Okay? And ghost vacuum times matter 1 primary, subject to the equivalence, primary plus descendant is the same as primary.
Last day you proved this, the S equal to 0 sector is the only relevant sector.
Yes.
And this S equal to 0 sector had no ghost, no
Well,
plus, no minus.
Well, we have to be a bit careful because S equals 0 is the only relevant sector for the simplified Q. Q1.
And then you had an argument because of the mapping that it's the same Q1 cohomology is Q cohomology.
No. Q1 cohomology
One-to-one
maps to Q cohomology.
Yeah, one-to-one maps to Q cohomology.
Yes. So we're going to use that, but go on.
Now you want to put little bit more that Q cohomology actually this one-to-one maps gives something
I don't.
that is also in this form.
That's right. That is always a representative in Q cohomology that is in this form. But you've intuited the right thing. What we're going to show, we had an explicit construction. How did we prove it? We didn't behave like mathematicians there, right? We just constructed it. And now I'm going to try to show you that in fact our construction is of this form.
Oh, okay.
That's what, more or less what you were saying. Okay? So let me remind you of our construction. Our construction was you start with the kind of states Indranil likes. So the states that were annihilated by NLC had no B ghosts, no C ghosts. And then you act with n is equal to 1 to infinity. What was it? S inverse u, n is equal to 0. Yeah, maybe I'll write it more explicitly. So, 1 minus S inverse u plus S inverse u, S inverse u plus on. Now, I want to show you that these states are automatically of the form that they are in the ghost vacuum. Okay? We've already checked that these states are in Q cohomology. So if they're in the ghost vacuum, then they must be of the form ghost vacuum times matter primary. Because we've shown that any state that is ghost vacuum times matter is of the form ghost vacuum times matter primary. Okay? So all I need to do is to show you that these states are in the ghost vacuum sector. And I'm going to, one can of course do this also explicitly, but I'm going to use a very clever argument, one in Polchinski's book. And the clever argument is to look at a particular quantum number, which is n prime, which is equal to 2n minus plus nb plus nc. Okay? Now I'm going to have to remind you of the various things that went into our construction. We're going to focus on this quantum number, and the structure of my argument is going to be as follows. I'm going to show that every term in this expansion has n prime less than equal to 0. I'll show by formal arguments. But of course n prime is a positive definite operator.
So it has to be 0.
So n prime has to be equal to 0. And if n prime is equal to 0, then it has no minus excitations, no B excitations, no C excitations. So in particular is in the ghost vacuum. Okay, so that's going to be what I'm going to try to prove. Now let's see, how do I prove it? Firstly, psi naught clearly has n prime equals 0.
Yes.
Okay, because psi naught had no minus excitation, no plus excitation, no B, no C. So great, psi naught has n prime. Now I want to understand what is the quantum numbers of this u fellow.
You had 0 and minus 1.
Right.
A in that concept.
Right. Let's look at that carefully. S, of course. Remember that S had quantum numbers 0 under all of these charges, because S was, we had an explicit formula, was this number of plus number of minus plus number of B plus number of C, which commutes with all of these numbers. So charges of S are 0. That's irrelevant. It's all a question of the charges of U. Now what was U? Remember that we had Q was equal to Q1 plus the rest. Okay, so the rest is Q0 plus Q minus 1. And then we took Q1 commutator R. Q1 commutator R was equal to S, and let's call this guy Q rest. Q rest commutator R was equal to U, because we had Q commutator R was S plus U. Okay?
Sorry, R was only the dagger of this Q1.
Dagger under a particular operation. I'll list what R was.
Only Q1.
Of only Q1. R was, let's just write it down. Up to some constants, it was alpha plus minus M, B of M. Some of it.
Only Q1, right?
Yes, only Q1. Okay. So first, the easy thing is to find firstly the quantum numbers of R. So let's see. There are terms in R. Let's take the M to be negative. That increases B by 1. But A, so that's a B creation operator.
And annihilates minus.
And an annihilation operator for minus, exactly.
In minus is minus 1.
Minus 1. And so this guy has charge minus 1.
Minus 2 plus 1 plus 0. So it is minus 1.
Exactly. Right? Because it has plus, charge plus 1 under B, the term that had M negative has plus 1 under B, but minus 1 under minus 1 under N minus. Okay? And therefore was totally minus 1, because minus 2 plus 1. Let's look at the terms with M negative. Okay? The terms with M negative, sorry, the terms with M positive annihilate a C.
It's also minus 1.
So it's also minus 1. And destroy, so sorry, these guys are plus, so these guys are minus. So create a plus, it's irrelevant. Yeah, so it's also minus 2.
No, minus 1 is 1.
No, this is minus 2. Yeah, the whole thing is minus 1.
Yes.
Yes. So this part continues to be minus 2 and this part continues to be minus 1. Because it destroys a C and creates a plus. Oh, sorry. It creates a, it destroys a C, therefore it's minus 1, and this part is 0. Sorry. Yes.
It does something to plus, you don't care about plus.
It does something to plus, it doesn't care, you don't care, exactly right. This is just 0, and because it destroys a C, it's minus 1. Okay, so both kind of terms, M positive and N negative, give you R equals minus 1. So our quantum number of R is equal to minus 1. Okay? Now, what about the quantum numbers of U? So the quantum numbers of U are the quantum numbers of Q rest plus the quantum numbers of R. Okay, so what we have to do is figure out the quantum numbers of Q rest.
Minus 1 and minus 2.
Um,
The QS is going to be 0 or minus 1, but those combined is going to be minus 1.
well, we have to be a bit careful. So let's look at all the expressions in Q. We have C M L minus M. We have terms which are of the form C C B, where the things add up to 0, and we've got C0.
These are all possible terms in Q.
These are all the terms in Q. So now let's look at the terms one by one. What about C0? C0 should be thought of as, in our way of thinking, is a creation operator, because acting on the ghost vacuum, it creates something. Okay? So this guy has charge +1 because it has charge under NC, no charge under NB, no charge under N minus. Okay. Right. Now there is, let's look at these guys. Yeah. These guys, so for instance, you know, every way of looking at it will give the same number.
How do you, is this some statement that
Oh, actually,
if I commute with this,
actually, every way of looking at it will give the same number for NB minus NC. Okay, let's look at all ways of looking at it. Let's look at these two
because NB minus NC
commutes. Yeah, you're right. NB plus NC may not be. So let's say that we look at these guys, which is plus, plus, and minus. So the but okay, it's just a question of how many pluses and how many minuses, because we don't care which is a B and which is a C, because it's NB plus NC. Okay, so it's number of minuses minus number of pluses.
minus.
Number of minuses minus number of pluses. So it could be +1 or -1. You could have -3, -5, and plus.
What's the particular configuration in here?
Oh, no, it's in general.
Okay. Oh, it is that, okay.
Sorry. In general, this guy could have either charge +1 or -1. Okay? Then what about this guy? Okay, so yeah, so what about this guy? Now, it was precisely this guy that gave us Q1. This was the fellow that carried charge N light cone. This NLC equals 1. So let's be careful here. No, but every term in here, every term in this quantity. Oh wait, but what about an LM? Just a minute. Yeah. We have to be careful about this N minus. You see, schematically L minus M is equal to alpha mu minus M plus K alpha mu minus K, sum over K.
This guy commutes with this N plus minus N minus?
No, you see, this N minus doesn't count the zero mode. So we have to be a bit careful. What?
We're missing one term from the series because we don't have the Q1. One of the two zeros are not there.
Yeah, right. We're missing one term from this. Yeah, exactly. So precisely the term which had Q1 was precisely the term that came with, let's remind ourselves. Q1 was the term that had alpha minus
Alpha minus
yeah,
C M.
and C,
Minus M.
yeah, all, yeah, all M's, right? Because this came with a K plus, so it absorbed up the. So, okay, now this, okay.
This K plus is neutral or not?
K plus is neutral under
So
our.
why did you, just continue.
Just to show you that the.
Okay.
No, it was.
Sorry.
it was looking okay. Okay, so now I want to show that this, I want to check the charges of this part, omitting that term. Now first let's look at the charges of Q1. Let's look at the charges of this Q1, that should be easy. So suppose we take negative here and positive here. Okay, since this is positive, this carries -1 here. And since this is negative, it creates +1, so that's a +2. So that so this would have been a +1.
That is because S is charge 0 and R is -1. Therefore, Q is +1.
S is charge 0. Excellent.
R is -1. Therefore, Q is +1.
Excellent. Excellent. So this guy was +1. And I want to argue that there is no term with higher than +1 in anywhere else. In fact, this was the most dangerous term. This was the most dangerous term because it was okay. Anyway, let's just look. I want to argue that there is no term with yeah. So suppose we've got a actually even whether this is k plus or alpha plus will not matter. So the general structure of the terms, see, there are the terms without the plus minus. Those guys have a C, and they can have at most charge equals +1. Because if C is a negative guy, it will carry charge +1. Okay, so those terms have charge at most +1. Now we can ask, what about the terms with alpha minus m, alpha plus m minus k, ck. Okay, we could ask about such terms, and these terms will carry, let's see, suppose k is negative. So this guy carries charge 1. Then what about the term where this is negative and this is negative? But that you don't care about. What about the term where this is yeah, this is negative. The dangerous term is where we get something positive here and positive here. Or at least something positive here is potentially dangerous, right? Okay, what about if the term where you have something positive here? So m is positive. If this is
minus m, right? Bad one. If m is negative, then it creates minuses.
Yes.
Therefore, it increases n prime by 2.
That's
m is negative is the most dangerous.
Is the dangerous one, exactly. So this guy is the dangerous one, but if this is negative and this is negative, then that would become +3.
+3.
Now, why can that not happen?
Wait. The middle one is then positive, and then that destroys the negative.
Exactly. So if this is well done, yeah. So if this is negative and this is also negative, then this has to be positive. Okay, and then this destroys one of those, and so this guy is actually neutral under n minus. So that's NC equals +1. Okay, it's clear that no term will have charge greater than 1. And this is the most dangerous possibility. Stuff without the pluses and the minuses. Stuff without the pluses and the minuses. Okay, and there's one other thing that you could have looked at, which is where this was the 0 mode. Okay, so we could look at that, but then if it's the 0 mode, this is 0.
Yeah, but that will
so if this is negative, this has to be positive. So this is negative, would increase this by 2, but that would then decrease this by 1. So there are many terms with charges 1, many terms with charge 0 and so on, but there's no term with charge greater than 1. Okay? M negative, M minus k positive, and C negative. M minus k positive destroys a mode of alpha minus, and therefore it carries negative charge under alpha minus. So it neutralizes the charge of this being positive.
Alpha plus 0 is a relation operator. How should I think about it?
Alpha plus 0 should just be thought of as a neutral. Neutral. But if you have alpha plus 0, then these two have to be opposite to each other.
Then I agreed that if you ignore that, then you get 1. If you ignore that alpha plus 0 is neutral, then you get 1. This I agreed.
No, I'm saying even take into account that it's neutral. Okay, so this does nothing, but it's only 0. So these two have to be opposite to each other. Okay, and so either one of them is negative, one of them is positive. Okay, if this guy is positive and this guy is negative, so that creates a minus mode, so that gives plus 2, but this destroys one of these, so it gives plus 1.
So you get plus 1, this I agreed. If you say that alpha plus 0 is neutral,
Yes.
this I agreed.
Uh-huh.
I'm just asking alpha, what was the logic for alpha plus?
Because it's k0. We're looking at the oscillator sector. All of these are just the oscillator modes.
All of these are yes.
Alpha mu 0 is just the momentum,
Just the momentum which is neutral, which is
which had nothing to do with the oscillator sector. Right? It came from quantizing the 0 mode of the free boson.
nothing to do with those things.
Yes,
0 was omitted in that probe.
exactly.
That's
That's the point. Okay, and therefore, I'm sorry this has been haphazard, but it's one of these haphazard arguments. You have to look term by term. M negative, M minus k negative. Okay, so suppose M minus k is negative, then it does nothing because it creates a plus, but we're not counting plus. So this is minus 2, then this has to be positive. Sorry, plus 2. This does nothing, but this has to be positive. So it reduces it by 1. No, you can't have all. Sorry, what is your M negative?
M minus k negative.
Negative, and therefore k has to be positive because they sum to 0.
It is not summed to 0.
I wrote it wrong.
Yeah. Or
Sorry. I have to write it so that they sum to 0. I'm sorry. I meant to write it so that they sum to 0. No, forget these indices. What you have is 3 guys so that they sum to 0. Okay? So, though the argument was haphazard, you see we've tried to stress test it to the worst case, and we've come to the conclusion that every term in QRest, okay, has charge which is at most equal to plus 1. Therefore, U is at most 0. So U is negative or 0. Okay? And therefore, this quantity has charge at most 0, because the net operator has charge at most 0 and acts on a state with charge 0. So it's charge at most 0. But there's no state in the Hilbert space that has charge less than 0. And therefore, this state here has charge under this quantum number equal to 0. And therefore, it has no C oscillators, no B oscillators, and no minus oscillators. Excitations. In particular, it has no B and no C, and therefore it's the ghost vector. Okay? So we've concluded that this state that we've created is a state of the sort we wanted, namely matter time ghost vector.
Still you have to do some work. I mean, because you have not some classes or 0, so
No, but I don't need to show pluses as 0. All I wanted to show,
It's in the ghost vacuum, that I agree.
that's all.
But now because you haven't showed classes, so you have to still work little bit that what are exact and so on in this sector.
No, no, but we looked at all states which are the form ghost vacuum times any matter state.
Yes, so if you look at states which are ghost vacuum times any matter state, then you still have to run the arguments like which is there in null state, which is the one that you.
We've just done that, right?
Yes.
So I'm saying that we've gone through a particular theory, the theory of all states that are ghost vacuum times matter, and we found this is an example.
I
Okay.
agree, so but you did this in the beginning of the class because you did not ensure that plus and minuses are 0.
Yeah, it's not going to, pluses will not be 0 in the state.
Yes.
Yeah, so it's going to, so exactly, okay, fine. And there, so what have we concluded? We've concluded that every state in BRST cohomology has a representative of the form, okay, which is ghost vacuum times matter. So if we're interested in scattering and we're not perverse, so we don't want to use that freedom for some particular reason, we lose nothing by sticking to states of the form ghost vacuum times matter. Of course, it has to be BRST closed, which means that the matter field has to be 1, primary. And if we choose to change that state by something that is a primary plus a descendant, something that's a descendant, okay, we will also find that it doesn't matter. So the remnant of this BRST exactness is in the freedom to add a descendant to anything we've done. And the remnant, the fact that it was BRST closed was the statement that it was a matter 1, primary. And this whole analysis has basically assured us, A, that on this space all norms are positive definite, and B, that by restricting to this class, by working with just ghost vacuum, we've not lost anything.
But if I start off with a matter primary, right, and then I want to excite a matter oscillator above it, right?
Mm-hmm.
It's no longer primary, because then it's a descendant.
Typically, it's no longer primary.
So then are these states?
Do you,
So what's the story with these? Yeah, with the excited states.
you want an example of a state that is both a descendant and a primary. Is this
And
what I'm
not
hearing
null.
from you?
Right, and not null.
No, it will always be null if it's something that's both. We showed sometime in this.
Yeah. So that's why I'm confused about. We're saying that all the states in the cohomology have to be primaries.
Have to be primaries.
And what happened to all the descendants? I mean, every excited oscillator is a descendant.
Right. Those are not allowed states for scattering.
I just want to know that hear that was true. Okay.
That is true. That is true. Okay. This is the analog of the fact that physical states had 24 excitations,
Yeah.
not 26.
Okay. These are oscillations in the plus minus direction.
Yeah.
Oh,
it is.
yeah. Okay. Then, yeah.
Okay. So the map between physical states in space-time and states on the world sheet are not mapped from that's 1 to 1. The physical states in space-time map to matter primaries, modulo those primaries that are also descendants.
So if I excite an oscillator in not the plus minus direction, some other direction, that will still be a physical thing.
If I excite the
Excite some matter oscillator not in the plus minus direction.
In the transverse direction.
Yeah.
yeah, you see the fact that we have shown that there is a 1-to-1 map between light cone gauge Hilbert space
Yeah.
and states in BRST cohomology
Yeah.
is the precise version of your statement. Okay, there's a labeling of states
Yeah.
by the oscillator excitations in the transverse directions. Okay, and how do you build a state out of that state? By acting with this operator. It's all very explicit.
So that's the entire S equals 0 space.
That's the entire S equals 0 space, which is light cone gauge quantization. Now, S equals 0 by itself is not in BRST cohomology, but the state is.
That's tilde equals 0.
this state is like the following. I don't know if you remember, but when we worked in light gauge, by definition, the alpha minuses, the n minuses were 0. Because our string just went zoop in the light cone direction, didn't wiggle in the light cone direction. Because we chose.
Yeah, that was the gauge fixing.
That was the gauge fixing. Okay? But it wasn't true that this x pluses were trivial. X pluses we solved for. The quadratic expressions in the xi's.
Your gauge fixing on x minus is something.
X minus is something.
That was your gauge fixing.
Exactly.
Okay.
Yeah.
And then x plus you solve by a quadratic.
We solved by the constraint.
From the t.
Exactly.
From the t you solve for x plus.
You solve for x plus, and because the t thing is quadratic in xi's, but linear in x plus, because x plus times x minus, and x minus is something very simple. Okay? We got a relationship for every x plus oscillator in terms of bilinears of xi oscillator. So it wasn't that the x pluses were doing nothing in light cone gauge.
They are completely determined by the.
They're completely determined. This is exactly what's going on here. You see, these states don't have n plus equal to 0. But they do have n minus equal to 0. So we started with a state which was fiction. Right? It had the same labeling of quantum numbers of light cone gauge, but wasn't the state of light cone gauge. Because we actually set all the x plus oscillators in this S the S eigenstate, all the x plus oscillators were also 0. We know that in physics that's not the case. Okay? But we showed that there is a one-to-one map within cohomology. What's this? This is solving for x plus in terms of the xi's. Okay? So that's what this fancy construction does.
Fancy construction and some x pluses exactly as needed to be consistent with that constant equation.
Exactly. In fact, we know that that's the case because the constraint equation is t is equal to 0. Okay? And the fact that these are matter primaries is imposing that constraint. And there, it's
Yes. Sorry.
yeah. The creation part of T is annihilating the state. Exactly. So this is a fancy version of doing that. So what this is doing, our construction really is producing the states that we produced by light cone quantization, but in a new fancy language. Then the fact that there is this ability to move by adding descendants tells us that we needn't have worked with exactly those states. We could have turned up, it sounds very crazy, right? Why are we singling out x minus rather than x plus? That was totally our choice. Why did we choose the 0 and 25th dimension to make x plus and x minus? We could have chosen 0 and 24. That was totally our choice. The fact that this is actually one representative in a structure that's completely Lorentz invariant is very nice. That is one way of functioning, but you could function every other way. And the class is completely Lorentz invariant.
Could I say the following? I could have done the same thing with q minus 1, cohomology of q minus 1.
Yes.
Set up a one-to-one map with this space.
Yes.
And then I would have replaced in n prime n minus with n plus.
Exactly. You would have done that. So that would have been another construction. You would have made a correspondence with another light cone gauge. Namely, x plus is equal to something simple.
There is no partiality between.
No partiality. Or, of course, you could have just defined your NLC differently.
Yes. Then you can. I kept all the definitions same because otherwise you have to.
Yeah, but you could rotate from x25 to x24. You could do whatever you want. All these constructions will go through for any of them. And we want to be guaranteed that we'll get the same answer no matter what we use. And the guarantee is this, that they're all parts of the same cohomology. That there's one structure, namely the cohomology in the sector which is matter times ghost vacuum. That encompasses these all. The invariant thing here is that they're all ghost vacuum. The rest depends on choices. And we see that the choices don't matter. Is this clear?
Let's say T on the state is not really 0, T is just exact. T on the state is exact. The top line.
Sorry,
The fact the top line is saying that T on a state is just exact. L minus K, right?
This is a particular kind of state that you can add to, that you can add to a matter state and not change anything.
But that's what if I would act with T on a state, it would just be a whole bunch of things like that.
It would be a bunch of things like that. That's correct. And adding that, if you add that, suppose I add this L minus K of chi, actually by chi it's absolutely anything.
Right.
And you take the inner product with a psi, which is a primary. Okay? This would be L k on psi, which is 0. This is the reason why adding such a thing to one of these states does nothing. Were you asking something else?
No, I was just saying that the statement that T on a state is equal to 0, we're really just saying that T as an operator equation acting on a state equals 0 is the same thing as saying that T on a state is 0.
Ah, that's what you're saying. Well, I was saying the following. I was saying that that's correct. That's correct. Since we're working with these primary types, we're always taking inner products with primary type states.
Yeah.
If you act with T on the state, you don't get 0, but you get a null state.
You get a null state.
Okay, and therefore it's equivalent to 0.
So as an operator,
Yes. It gives the same matrix elements as if it was 0. Excellent. Yes, well said. Okay, other questions, comments?
In scattering,
Yes.
if you have quantum loops, if you have loops,
Yes.
then things go offset in the middle of the loop.
Yes.
All these things are about on-cell business. So if if I understand wrong, you will tell me.
No, what you're saying is right.
So everything looks like some on-cell everything is good.
Yes.
But if you calculate scattering matrix,
Yes.
then in the loops things will go off-cell, and then is it clear that it will not interact with any ghost or anything?
Yeah, this is something you have to prove.
Yes, it's not obvious, right?
It's not completely obvious, but you know,
But how do you go about even in principle?
well, just first to respond to that, you could ask the same question in gauge theory.
Yes.
Okay, in gauge theory, off-shell amplitudes are meaningless,
Yes.
and so you might have the same kind of worry in gauge theory. In gauge theory. Okay, and yet we know that it works out. So now, how do you go about proving this? Well, what you have to show is that the integrals that appear in the string scattering amplitude, okay, what you have to show is factorization basically on without the ghosts. See, for instance, the thing that you have to show is unitarity. Right? This is the precise question you're asking. You're asking, are Kutkowski's rules obeyed?
Even in a gauge theory, I don't know gauge theory is good. So let's say in non-abelian gauge theory,
Yeah.
stay away from gravity.
Yeah. The way that the standard way of proving this is this.
Yes.
Okay, the standard two-line way of proving it.
Yes.
Go to a gauge where there are no ghosts. Then it's clear. What's not clear in that gauge is there is Lorentz invariant. But if gauge invariance is correct, there's a gauge where it's obviously Lorentz invariant, a gauge where it's obviously no ghosts.
This is like totally not the kind of.
That's not what you wanted. Yeah.
Totally like an argument. Is that an in principle argument? How do I prove
He wants to know that if you cut a diagram, how do I know that I will not get that I will not get ghosts running somewhere.
But in regular quantum field theory, we let ghosts happen in the loops.
Right.
We just show that they can't show up in the end.
No, but they also shouldn't show up in the cuts. In
Yes.
you see, this in Kutkowski's rules, they should not show up. You see, it's true that the Feynman diagrams have the ghost running in loops, but now these Feynman diagrams sometimes have singularities, and the coefficients of these singularities, okay, obey unitarity. And you cut this way. The singularity of this one loop graph should be obtained by putting together these two graphs only with physical states.
So you're saying that even if I wrote down a term that had a ghost in the middle, there has to be an equivalent two terms that I could write down without ghosts, that when I put them together I should be getting effectively the same thing?
Exactly, and the way it works in Lorentz gauge, for instance, is that the unphysical polarizations of the gauge field, so you see, in Lorentz gauge what you have is four things happening. A, you have the physical degrees of freedom. You have the unphysical degrees of freedom of the gauge field. And you've got the ghosts. And these two cancel each other out. That's what's going on.
That's not going, if you calculate some diagram, then probably you will see
This is what you see.
explicitly, but I was asking for some in principle argument.
The argument is what an argument is what I gave you. That it was a gauge invariant, it can't. Yeah, it can't. There's probably something better to say.
I think this was a work of Professor over the last couple of years in proving the Kutkowski rules for superstring.
For string field theory.
String
Yeah, but what Indranil is asking, just in gauge theory, nothing so fancy. Can you see it completely explicitly? There's probably something.
What is the structure of the argument?
But I've given you an argument.
Okay, fine, let's not ask this.
Yeah, if you want to try to prove it, Feynman what you now want is some Feynman diagrammatics, right? You want to see diagrammatically. I suppose that's what you're after. Oh, okay. I'm sure it's possible. In string theory, at least intuitively, I will give you. Basically, the paths that involve these ghosts will cancel out when you do the right integrals. I will try to show you that, at least intuitively. Okay, there's probably some version of that in gauge theory. I don't know. Yeah. Diagrammatically, I will, at least roughly when we come to it, I'll show you. Yeah, I'll show you how it works. Okay. Yeah, okay, fine. Anyway, fine. It will mirror a world sheet OP structure. Let's see if I can say something immediate. Just the dangers across terms. Let's yeah. Okay. That's all I wanted to say about ghosts and BRST symmetry and the no-ghost theorem. Okay, now that we understand all of this, let's go back to our formula for string scattering amplitudes and look at it once more. Okay. Okay, so I'm just writing it down. Okay, then there were the insertions. The insertions were the moduli.
Mu number of derivatives.
Exactly. So B del kg.
Mu number
Product over I is equal to 1 to number of moduli. This B del kg. Then we had product over the number of CKVs.
number of conformal killing vector number of C.
Yes, I the number of conformal killing vectors. We have C I of sigma I, some fixed values. Square root G of sigma I times V of sigma I, the corresponding particle, and we have product I is equal to number of CKV plus 1 to whatever, however many other particles you have, integral d2z square root G d2x d2 sigma square root G and V of sigma. This was a string scattering formula. Okay, now we're going to look at each term in this formula once again just to make sure we understand it. I mean, the terms that we're really interested in at the moment are those involving the V insertions. Notice that this C times V, okay, is precisely of the form of a state and BRST cohomology if V is a matter primary.
V is a matter primary, then Q annihilates it.
Then Q annihilates it. Okay.
One.
What? Yeah. So the rule we're going to take is that V is equal to matter primary. Modulo things that are matter descendants. Okay?
Matter primary of dimension 1.
Of dimension 1. Modulo, I'm not going to write it, but modulo matter descendants. Okay? And there are many things we want to check. One of the checks is that, okay, good. This guy here will give rise to BRST invariant insertions. Okay? But what about when I act with the BRST operator on this guy? Yes, we did. I can't remember. We showed that?
Yeah, totally.
Excellent. So we acted with the BRST operator on this guy. This guy was a matter 1 primary, and we got a total derivative. Since this guy appears with an integral that was also BRST invariant, after doing the integral, provided all boundary terms cancel. At this level, we're not going to look at this argument. This is the kind of thing Ashok has done very carefully, the boundary terms cancelling. Okay, at this level we're not going to look at that. Boundary terms cancelling very carefully. We'll see in examples though why that's not too unreasonable. We'll see that the integral that we have to do is an integral over a compact moduli space in general. However, these moduli spaces sometimes have singularities associated with IR divergences and so on. Those are the things that are the subtleties.
Moduli space of what? Like the original, the Diffio and Weil modular space, or this is a new modular space?
Well, at the moment, this integral, you know, the way we've said it, this is just the moduli space of where you're doing the integral over. Right? So it's just, naively speaking, it's the moduli space of the insertions. So just the space. Okay? But the problem, the issues are, can bang on to each other. So is it effectively compact? Are we going to get some contribution, an effective boundary term from a singularity? These are the kind of issues that you have to worry about. Okay? I'm just going to ignore all such things at this level. We come back to these things in special examples, and next semester if we continue our course and want to go that way, we'll try to go through some of Ashok's papers on this, where he really checks all these things very carefully. Okay? Great. So this is the rule for the string scattering amplitude, where V is now taken to be a 1-over-1 matter primary. Now, there's one other thing that I wanted to say. Okay, so you see, now we've established that the set of things that we put in here are in correspondence with the light cone gauge quantization of the string. So the set of things that we put in here are the things that we expected to scatter. Okay, and we're going to do this. This calculation has to be done with any representative of the BRST cohomology corresponding to the stated question. That will give you the scattering amplitude for those physical particles. Okay, there's one last thing I wanted to say about this formula, which concerns this part of it. Okay. This integral over over these t's and this part of it. Okay, and that last thing I wanted to say, and that ends our formal discussion of this amplitude.
So far you have never said anything about regularization or anything. If there will be divergences, then you need some regulator, all these things. And
right. So there are two. No, so there are only two kinds of divergences. There are divergences when operators go and hit each other, or there might be divergences associated with the integral over moduli space. That T. And actually, if we were mathematicians, or if we were even very careful physicists, you know, there is a way of thinking of this whole integral as an integral over a single moduli space. You see, because what we're doing is, let's say we've got 4 operators and we're integrating over the positions of 4 operators on, let's say, a torus. What we're doing in effect is an integral over what?
Over, I mean, T8.
Yeah, right. No, I know what you're saying, but actually, you know, we have to do the integral over the moduli space of the torus and the insertions of the operators. Now, you know, mathematicians have a way of thinking of this problem. They think of a torus with 4 marked points.
it's not a torus, something else.
It's something with as you were saying, a 10-dimensional moduli space. And they think of that whole moduli space as coming together. You know, not separating it into integrating over the moduli of the torus and the moduli of the points. Just one big moduli space. And there are some advantages to thinking that way.
But then you need to write down the suitable measure of this moduli space.
Yeah. So but in our way of thinking of this moduli space, which at least, you know, in open neighborhoods we can always do, we've written down the measure. And that defines it.
In your 10-dimensional space. So this measure will go to some different measure in this 10-dimensional space, in this new space.
Well, this is the whole measure. We've got an integral over 10 dimensions, right? There's d2t, and 4 d2 sigmas. So that was the 10-dimensional space.
That is the 10-dimensional space. I thought you wanted to go to a.
No, it's just a more abstract representation of the 10-dimensional space. In our way of parameterizing it, we've got a measure, and then some lifting of that to some more abstract stuff. Yeah. So I'm saying that what I wanted to say was that the singularities of that, the singularities associated with squeezing of moduli, and the singularities associated with points coming together, they treat on some equal footing. Okay. Now, in our situation, each of these singularities will exist and will have meaning. Okay. So there's no regulation apart from the only when we encounter singularities, we will just demand analyticity. That will be enough. So, for instance, when 2 points come together, this will be associated with the singularity of a particular particle being produced. So suppose I've got O1 and O2 coming together. Exactly. So we get some OM by Z to the power M. Let's say this is dimension 1, you also have the dimension 1 guy here. We'll see that these singularities will lead to physical singularities in full scattering amplitude only when this is dimension 1. This is part of what you were asking about non-physical states not contributing to Kutkowski's rules.
Because this OM has to be dimension 1.
Oh, has to be dimension 1.
And O1 or 2 is dimension 1.
Exactly. So you'll get this 1 over Z. And when we get associated with such a singularity will be a diagram like this, where OM runs in the middle. So we'll get some singular effects. We'll get some effects on our scattering amplitude, which will be interesting singularities, but those are precisely the effects that are needed for spacetime unitarity. Okay? Similarly, when we look at the integral over moduli space, we go to regions which are potentially singular. Sometimes there are singularities, but we'll understand each of these things in physical terms. So all this is coming. Yeah. We'll look at all of the. We'll study this formula in great detail in many examples.
But in our class so far, you haven't said anything about DT.
DT.
How to calculate them?
This one. No, this is the measure. You can choose any parameterization of the moduli space, and this was invariant under change of coordinates.
Because this derivative of G is with respect to T.
Exactly.
So this exactly as many things.
Yeah, you remember we wrote this like a determinant, and we showed that it transformed in exactly the right way so that it did not change under parameterization.
You just cancel.
Those cancel. However, there is one thing I wanted to say about that, and that is this. You see, there is one quick thing, and then we'll move on. And this quick thing has to do with processing this quantity. So suppose we take this object, which you will remember was square root G B mu nu del K of G mu nu. That's what del by del Tk. That's what that quantity meant. Okay. Now, let us remember one thing. One thing to remember is that this quantity here is traceless. This B mu nu is traceless. Okay? What does that mean? This means that suppose we took G mu nu and made it G mu nu times e to the power phi of k. Phi k of x, something. That is this one parameter set of metrics. Okay? If it involved just taking the original G mu nu and changing it by a Weil factor, then we would get something times G mu nu times B mu nu, which would just give us 0, because B was traceless.
Sorry. The derivative with respect to T,
The derivative with respect to
K does not change anything.
Tk acts only on this whole
Exponential.
thing, because nothing else cares about K. So the point is that the index structure is that of G, and therefore it would continue to contract with B, and so you get 0. And this is of course how it should be, right? Because remember, what were the TKs? TKs were labeling metrics that were while and diffeomorphism inequivalent. And clearly if I just did this, these two metrics are not while inequivalent because I've just done a while transformation. So if I by mistake choose a larger set of metrics than I should have, the physics, our formula will tell us that I don't have to integrate over that larger set of metrics. Okay? So these.
Diffeomorphism is not as clear to me.
No, diffeomorphism will also preserve the symmetry structure. Yeah.
Well, no, what we're using over here for a while is that you can basically pull the G mu nu out and get a zero, right? But if I did a diffeomorphism, I should also get zero somehow from this.
Let's do it. So suppose the change in G is by a diffeomorphism. So the change in this action, this derivative with respect to K, will give us B mu nu del mu zeta nu. Act on the.
Right, symmetric and anti-symmetric.
No.
So that's not let's trace this.
This is just any zeta. It's not a Killing vector. Okay, but integrate by parts and use the B equation of motion. Okay, so the B equation of motion, which is del mu B mu nu is equal to 0, okay, will basically make this, will ensure the diffeomorphism invariance. Now actually there is a bit of a subtlety in this argument that I encourage you to work out. Okay, and that subtlety is that we're using the equations of motion. But we worked out in class how one should correctly use the equations of motion. Correctly using the equations of motion involves contact terms. Now, correctly using the B equation of motion, okay, correctly using the B equations of motion could involve a contact term with a C. Right? Because let's remind ourselves how in a path integral we got a B equation of motion. Okay, we got del by del C mu, C of sigma.
This B has dimension -2, which is upper B. This B upper quantities has dimension -2, and then it can have a C in the right hand side because that del mu probably have dimension 1. Why did you say
No. I'm not going to say that del mu B mu nu will have something on the right hand side. I'm saying del mu B mu nu is equal to 0 will be correct up to contact terms.
Yes.
Okay, so that's the thing we're worrying about at the moment. Not that it's not 0, but that when in the presence of other operators you might get contact terms.
Yes, and you did not say that this contact term will involve C.
The contact term will involve, let's just work it out too. I'm working on the ward identity. So consider del by del C of e to the power minus s. That when acting on this s will give us a del mu B mu nu. But now suppose I had an insertion of a C. Suppose I had an insertion of a C, that thing would give us a delta function. So we'll get del mu B mu nu C plus delta function is equal to 0. So inside a path integral which involves an insertion of a C or insertion of many C's, there are many possible delta functions. Is this clear?
Yeah.
Okay. Now the danger is that this path integral that we're looking at does involve the insertions of C's. Okay. So using equations of motion without worrying about contact terms is a dangerous game.
Can't we use the gauge invariance to just move it away?
Move it away. Gauge invariance. So at the moment we've got a formula and we just want to check that it's diffeomorphism invariant. Can anyone tell me? Let's, maybe there's some philosophical thing, but I should be able to see by doing a diffeomorphism transformation. Okay? Of course, this term is diffeomorphism invariant. But there's something else here that's not diffeomorphism invariant. The terms with the insertions. Okay. Now, what will the change of this be? Yes, exactly. So this is the exercise I want to leave you. You see, because a diffeomorphism will move this insertion just by a little bit. Okay? And I would like to request you to check. Okay? I want you take Yankee's question and show it carefully. Show it that including the presence of contact terms, including the contribution from contact terms, you can show that this answer is diffeomorphism invariant, in the sense that you make a change of everything, of the background metric by diffeomorphism, you will not change your answer. Okay? You have to take every element in the formula and you'll check that it's true. This is a great exercise. Please do it. Please do it, and if there's anyone who has trouble, we'll do it in the next class. Okay, but let's come back to what I was going to say, what I was trying to say. Okay, so yeah, so what I was trying to say was the following. See, this object here, of course, gives you something 0 when G is just while transformed. Okay, so now I want to use that idea to rewrite this formula in a slightly more intuitive way. Okay, and what I'm going to do is the following.
This was diffeomorphism invariant because there was an integration. This product or modular B inner product with del K Z was diffeomorphism invariant because there was an integration.
No, but you know, you have to now, what we want to do is the following. No, you have to be careful because there's the del K. Let's say to start with we want to do this, that if we change background G by a diffeomorphism,
okay,
let's suppose that we change background G by a diffeomorphism.
That we can do because we fixed it by our will, some particular G we fixed.
Yes.
So we
Now,
can change it by something.
it should not matter, the formula should not care about what that G is if we change it by either while transformation or by a diffeomorphism.
Now, because we are changing background G, so this term is contributing something. This B del K G contributes something.
Right.
And square root G also contributes something.
Square root G also contributes something.
Others are manifested diffeomorphism.
Exactly. Exactly. That the change in this will cancel the contact term because of this. That's what you have to check. Yeah.
Background.
The background thing. Now there's another thing that you could also check, which is that the answer doesn't depend on, for instance, the location of this sigma I. Okay, I'm listing a couple of I'll list 3-4 exercises. You guys check them all, and anyone who has any trouble will check it in class. Okay, so X, move point of insertion by zeta I, some infinitesimal vector for one of the inserted operators. Check that the amplitude doesn't care. Okay. Another exercise is what we just said, that is change background G. Change background G by while plus diffeo check that the answer doesn't depend.
So first one can be done for any particular sigma.
Any particular sigma.
This is
It's more general than doing just some diffeomorphism. Yeah. Okay. And let's see, is there a third thing I want you to check? Okay, let's try this as well. Check that you get the same answer if you flip which operator is integrated over and which one is fixed. Well, let's say we've got 4 vertex operators on a space where you have to fix 3 of them. Okay? So we can choose any one of those 3 to be fixed operators and the 4th one to be integrated.
I mean, it seems like these are all 4 copies of the same. Like, I don't know, right? I'm given 4 V's.
But they could be distinct V's. Oh, one of them could be a tachyon, the other could be a graviton. One of them carries momentum k1, the other carries momentum k2. They're distinct quantum numbers. Right? So it shouldn't matter where I put, which one I fix, which one I integrate over. Okay? Check that you can prove all of these. Okay? And any assignment that has any confusion, we'll discuss in class. Okay. Now I just wanted to get back to this part of that formula just for 2 minutes. And that's the thing I wanted to understand, I wanted to say was this. Look, we are interested in the space of metrics that you can put on this 2-dimensional surface, modulo, of course, diffeomorphisms, that's given, but also modulo Wild transformations. Okay? Now, modulo Wild transformations in a little patch. A little patch of any space can always be put in the form dzi dz bar times e to the power some phi. Sorry. Hello? Probably. But I'm teaching a class now. I'll just call you later. Yeah. Okay. So, right. So any manifold can be thought of as dzi bar times e to the power phi. So what we can do is take any manifold and glue it together. Break it up and cover it with patches, such that on each patch, the metric takes the form dzi bar times e to the power phi. Okay. Now, what is of interest is that you cannot do this globally. Okay. This is the thing that makes the manifold have a non-trivial moduli space. And the ways of patching together the z's in this patch with the z's in this patch
Will have some transition function.
right, has some transition function, and the inequivalent ways of writing down those transition functions are essentially capture the moduli space of the space. Now what do I mean by inequivalent? Any way that just changes the phi's. Okay? Any way that just changes the phi's, any way that just keeps the structure but changes the phi's is not doing anything. That's just some wild transformation. Okay? That tells you that if you do some sort of holomorphic suppose I have Z here is holomorphically related to the Z in the next patch. Okay? That will keep the relationship between, let's say that on the first patch we had Z's and the second patch we had W's. Now we make effectively W a function of W prime. That will give us a new transition function between Z and W prime, but that will not give us a new manifold, because all we're doing is a wild transformation on the second patch. Okay? So the transition functions that will be of importance, the changes in transition functions are the changes that mix a holomorphic coordinate on one patch with the changes that changes what is holomorphic.
So when you go from one patch, let's say if I have Z on one and W on the other.
Yes.
It's meaningless to say that Z here is going to W or Z is going to W bar, right?
Yes.
But they're just sort of, let's say if you go around an entire circle and suddenly you realize that I went from Z to W to X, whatever, and then I come back, that whole chain ended up with my Z going to Z bar. That's when I sort of ran into trouble, right?
Yeah.
It will be a general function of Z and Z bar. I mean,
Yeah. It's true that the final information will be more global. But just at the level of putting two patches together, if the coordinate change from Z to W changes in a way that involves a W bar.
Yeah. Right. You want one coordinate to be a function of one coordinate and then keep that pattern going.
Exactly. That is
trivial while trans.
no. In a way, that's a function of W bar. That's a non-trivial.
Yeah, I mean, the W bar, when you include the W bar, I mean,
Yes.
when Z, it's only Z as a function of W, that's trivial while.
Exactly. If I change it so that Z of the old Z and the new Z remain holomorphically related. Let me say this in formulas, it will become clearer. What I want to do is to take this object here and rewrite it in terms of these transition functions going from patch to patch. Okay, so let's write this in formulas and then we'll say the words. It'll become a bit clearer. Okay, so see, what I have is the following. What I have is on, let's say, patch 1 and patch 2, I have a metric such that on patch, firstly I have coordinates. On patch 1 I have coordinates Z1 and Z1 bar. Okay, the metric takes the form dZ1 bar times e to the power phi 1 of Z1 bar. Let's suppose that's the case. On patch 2, I've got Z2 and Z2 bar, and the metric takes the form e to the power dZ2 bar e to the power some phi 2 of Z2 bar. Now, suppose I do the following. Suppose I change the definition on the overlap region, Z2 is some function of Z1 and Z1 bar. Okay, whatever, it's some function. Now, suppose I change that definition in the following way. Z2 was the old Z2. Okay, so delta Z2 is equal to some new function which I'll give a name to. Z2 is equal to Z2, the old thing. Oh, so Z2 goes to Z2 plus, and then delta T, some change in the kth modulus, times Vk of Z and Z bar. This was Z1 and Z1 bar. Okay, so I changed the definition of Z2, which was the old Z2, which was whatever it was of Z1 and Z1 bar, plus a new function. Okay, and I do nothing. The metric continues to be dz1 bar on the first patch, and dz2 bar on the second patch. What? What? Yeah, they can do whatever they do. That they dz2 bar times something, it makes no difference. The e to the power 5 factors will make no difference, right? Because it's just a Weyl transformation. Okay.
Vk depends on what Z1 bar is. Okay, let me just hear.
Yeah. Okay. Now, suppose we make such a change. This tells us that the metric on patch number 2 so this was 1 and this is 2. The metric on patch number 2 that changes some, was dz, is dz this whole thing, right? dz2 plus delta tk. Now, del z vk plus
Del Z1.
del z, yes, vk is a function, times dz1 plus del z2 vk times dz2. So changing this, this map between Z1 and Z2, and whether you keep this Weyl factor the same or fix that doesn't matter, is equivalent to changing the metric. Okay, changing the metric on the second patch, and the change is by dz is Weyl equivalent to dz2 times the bar part of this.
I think that would be Z1 part, the second.
Z1
yeah.
bar, yes. Z1 bar. dz, and then at this level, dz1 and dz1. Just confused. Just a minute. Sorry. Let me back up. No 1 and 2. Let me just start as follows. Suppose I've got a patch here. I'm sorry. We come to transition functions in a bit. But suppose I've got a patch here and my coordinates are z and z bar. And I've got some e to the power some Weyl factor. Now, on this patch, I'm going to forget about the transitions between this patch and the next patch for a moment. On this patch, I do the following. I do z is equal to z plus what I had before.
Modulus.
Yeah, z is equal to z plus del tk del k of v of z bar. So now there's no z1, z2, it's just a z on just a given patch. Okay? And I keep this guy fixed. Not that it matters. Okay? I want to know how much that change of coordinates changes the metric. What? Yes. It is a diffeomorphism, but you know what I'm going to be doing is a diffeomorphism on one patch, but not necessarily the same diffeomorphism on another patch. Okay? So that relative thing will matter. Okay? So suppose I keep, right.
I mean, the essential part is that you are not changing the while factor, which...
No, the while factor actually is playing no role.
I mean, the while factor will change because it's a function of z that changes, so
Yeah.
Yeah, that's what I was...
No, that's not the important thing. The thing is that we're going to be doing diffeomorphisms patch by patch, and on the overlap we won't necessarily be doing the same diffeomorphism.
Right.
So this is actually physical. But right now I'm just looking at it in a patch. You see, we want to be doing diffeomorphisms on this patch, another diffeomorphism maybe on the other patch, and then we'll be putting these two things together with some transition function that will not necessarily change according to these diffeomorphisms.
Right.
So now then on the whole manifold we're changing something. Right? So patch by patch we're doing nothing. Okay? But once we patch together we're doing something. Okay. So the first thing that we want to do is to try to understand how the metric has changed up to while transformations due to this thing. Okay? So the change in the metric delta.
Why did you take this function?
What?
Derivative of a function? Why did you take this? Is there any reason in particular?
Because you know you've got to
Shift of the moduli.
exactly.
Oh, wait. So this v is a function of t.
This v is a function of this.
Some number of parameters.
Yes.
This v is a function of t, but okay, just we can at the moment just call it t vk.
Exactly. Now I have nothing to say.
Yeah, it's just one parameter thing. Sorry. Yes. Okay. Now let's look at how the metric will change. You see, the metric which was just as a function, how it will change. Okay. The metric which was dz bar picks up a term which is dz times dz bar from here, and vice versa. Okay. So the change in the metric just as a function will be dz. Okay, but you know, the change that is proportional to dz bar, that's a while transformation.
Yeah.
That we're not interested in. We're interested in the part that is
Diagonal.
dz squared and dz bar squared. Those are the parts that are non-trivial, that are not just while equivalent. Right? So the change in the metric will be, so delta of this line element will be dz squared times delta tk del z of vk z bar, no, del z
the whole quantity squared.
d,
Yeah.
no, I want the dz bar part of this, so it will be dz bar of v bar dz of v bar.
The square part of this.
Because we want the coordinate change in z bar, right?
Oh, right.
Let's write it out properly.
Yeah.
So z is equal to z plus delta tk vk of z bar, and z bar is equal to z bar plus delta tk of vk bar of z bar z. Let's say some real coordinate change. Okay. Okay. Now let's look at the change in the metric. Okay. This will be delta of the metric, delta GZZ will be del, yeah, by del Z of V bar K Z bar Z times delta Tk. What? V bar of K. And delta of G Z bar will be delta Tk del Z bar. Yeah, del by del Z bar of K of Z bar.
And you have a change in GZZ bar.
That is absorbed in a shift in the while factor.
Yeah. I want to.
Go on. Go on.
So anything that we have, you can make a coordinate expression and absorbing the while factor. When you say that you are absorbing the while factor, what do you really mean? I am not understanding.
Yes. You see, I am looking just at the space of while inequivalent metrics in some coordinate system. The coordinate system is important because I am going to look at relative transformation of coordinates between patches. So you see, it is true that I can get rid of this by a coordinate change, but that coordinate change will change the transition functions between patches. So imagine I have got a bunch of patches and I have got a set of fixed transition functions. Okay?
Yes, but if I do a diffio here, right, and then I do a diffio here, I can choose a while factor overall that will either get rid of the while part of here or the while part of here. It might not be that I can get rid of the while part of both of those.
I don't understand. Say that again, please.
If I do a diffeomorphism on this patch, right,
Yes.
you're saying, okay, but ignore the while part. And then you do a diffeomorphism on this part, and you say, oh, ignore the while part. Maybe you can't get a single while thing that will get rid of both of these, right? You're assuming that on the overlap, the only thing that's going to matter is this over here. Because it seems like you're simultaneously saying I'll use the while factor to get rid of it on this side, or I'll use the while factor to get rid of it on the other side. Right?
No, I'm looking at metrics that are any two metrics which differ globally by point by point by while transformation. So let's see, what am I doing? Yeah. Suppose, what are the kind of metrics I'm looking at? I'm looking at metrics such that it's dzi dz bar I times e to the power phi I of zz bar, zi bar on each patch. Okay? And of course, there is some map between the zi's and zi bars such that under this map, these two metrics are the same. Okay, where they overlap, these two metrics are related by a diffeomorphism. Right, that's the structure that we're looking at. No, we got the whole space, the metric on the whole space. It's come some given metric. Okay, on any patch, it's dz times dz bar times while. And it's a well-defined metric on the whole space. So the whole metric on overlaps after you make the coordinate transformation agrees.
Yes.
Okay, so that's the starting point.
Okay.
We've got a well-defined metric everywhere.
Okay.
Now, what I'm going to be doing is the following. There is on these transitions, there is some map between Z1 and Z2.
Yes.
Okay, that map together with these functions completely defines the metric on my space.
Yes.
Okay. Now what I'm going to be doing is the following. Now I'm going to be changing the coordinate. Okay, I'm going to be doing the following. I'm going to do a change in the metric on one of these patches as follows. I'll do a coordinate transformation on one of the patches. and not change the transition functions.
And which will,
new description now. Because the transition functions you didn't change. You changed one patch coordinate system, so it's a different kind of thing now you have got.
Yes, I've got a new metric. However, what I've done, as I said it just now, it doesn't make sense. Because if I change this coordinate function and not change the transition function, then the metrics no longer agree
Exactly.
on this overlap thing.
so it's a new manifold in a way. I mean, it's a more
No. Even as a manifold, I've not got a well-defined.
You don't
Yes.
have a well-defined metric on whole space.
I don't have a well-defined metric on the whole space. So I'm going to have to do these things in a coordinated way, so that I continue to get a well-defined metric on the whole space.
Yes.
Okay, but what I'm going to be doing is to be doing one of these changes here, another change there, so that I continue to get a well-defined metric on the whole space, but the way will not necessarily be the same diffeomorphism here and here, because I'm going to allow myself to do this and change by while factors.
While factors for transition. While factors.
While factors in this patch separately from while factors in this patch.
You will do one coordinate transformation on this patch, another one on that patch.
I will do one coordinate transformation on this patch. For each of these patches I'm going to do some sort of coordinate transformation.
Two different coordinates transformation on two patches, subjected to the condition that when they overlap, the matrices match.
Matrix match, exactly. So I've got
suitable language they match. This is the restriction.
yes.
And then what was the while condition?
Yes. Now I am really interested in if I have to do this coordinate transformation and change the while factor in a given patch, I will do both.
Okay.
I'll do this coordinate transformation plus a while transformation on my patch in such a way so as to arrange that the metric continues to match across patches. Okay, this will give me a set of new metrics. It will be a well-defined metric which will continue to match across patches, but will give me a set of new metrics. Okay, I'm going to build a set of metrics by this procedure and try to lay out the whole set of while inequivalent metrics using such a procedure. Only I'm sorry, I'm going to have to go very soon. So we have a class tomorrow, right? We'll finish this tomorrow.
Tomorrow when, sorry.
Tomorrow,
I think at the usual.
yeah,
Usual is 5 is
5, yeah.
I just want to be clear, I don't want to miss that.
Yeah. Okay, sorry, I'm going to have to go sort of now. We'll finish this quickly. But before I go, one thing I want to ask you, we'll finish this part and we'll reword this B thing in terms of what I call Beltrami differentials. This is what I plan to do. I did it very badly. Whereas this is what I plan to do fast, this class. Now, what I want to know from you guys is this. After we do that, would you rather start seeing physics with the bosonic string? But by which I mean, shall we start calculating scattering amplitudes? Shall we start seeing the bosonic analog of the Virasoro-Shapiro formula, the Veneziano amplitude? Start looking at D-branes in the bosonic string, things like that? Or would you like to do more formalism so that we move on to studying the superstring and then postpone the physics to after we finished that entire formalism?